Okay. Hello, friends, and welcome to this 6th installment of our webinar series on geology and the mining sector. Today, we are deep diving into geochemical surveys. We will also conclude our second block, which covered mining exploration, and we will move on to mining exploitation in 2 weeks from now. As usual, if you have any questions during the course of this webinar, just type them in the chat box on your right-hand side of your screen. If you catch this webinar a few weeks from now, feel free to write any questions you have to info@iddpnql.ca. And I think that pretty much sums it up. So I'll leave the floor to Francine. Take it away.
Thank you. So welcome to this new and final lesson of block 2. Okay, so I'm just going to share my screen. Here. Let's go here. Okay, so the lesson 3 of block 2. Going here. So it's the final block of the surveys. So we have seen the geochemical, we have seen, the cartography and geophysical surveys. So to finalize the surveys, today is the geochemical one. So like the others, they will be broken down into the following sub-lessons. Introduction to geochemistry, the overview of the field techniques, how we use the geochemistry data, and how these data are used to validate and interpret our geological surveys. So first of all, what is geochemistry? Geochemistry basically studies the origin, evolution, and distribution of the chemical elements of the earth, which are contained in the rock-forming minerals and the products derived from it, as well as in living beings, water, and atmosphere. So the geochemistry basically studies how our rocks, minerals are changing through time based on either temperature, pressure, and the environment conditions. So one of the goals of geochemistry is to determine the abundance of the elements in nature, as this information is essential to hypotheses development about the origin and structure of our planet and the universe. So geochemistry uses chemistry to understand various processes of the earth. Geochemistry is the chemistry of the earth's material, so the minerals and the rocks. So the study of the chemical composition of the earth and other planets includes the chemical processes and reactions that govern the composition of rocks, water, and soils, the cycles of matter and energy that transport the Earth's chemical components in time and space, and their interaction with the hydrosphere and the atmosphere. Here I present Mr. Victor Goldsmith, which is a Swiss chemist and is known as the founder, characterizing in 1933 the major role of geochemistry. So Mr. Goldsmith, what he did is that he investigated the composition of the earth as a whole and of its various components, and basically wrote the laws that control the distribution of the various elements. He based his studies and comprehensive collection of analytical data using terrestrial materials such as rocks, waters, and atmosphere. He also used meteorites, astrophysical data about the composition of other cosmic bodies, and geophysical data about the nature of the Earth's inside. Finally, he used information from the synthesis of minerals in the lab and from the observation of their mode of formation and stability compositions. To better understand today's lesson, I just went back from and just wanted to develop a little bit more when we touched within the first lessons about the Earth's interior, the Earth's composition. So here is a flashback to that. So we see here on the left the Earth with a pie cut within the Earth, and just to represent or illustrate how the Earth from the outer crust to the inside or the core, how the Earth is composed. So the Earth's crust is a thin, hard outer shell of rock, and under the crust there is a deep layer of hot, soft rock called the mantle. So the crust and the upper mantle can be divided into three layers according to their rigidity. The lithosphere is the upper rigid layer of the Earth, so it consists of the crust and the top layer of the mantle, so it roughly represents 100 kilometers thick. We then have the asthenosphere, which is below the lithosphere, and in the Earth's mantle is the hot soft rock of the asthenosphere. The boundary between the lithosphere and the asthenosphere occurs when the temperature climbs above 1300 Celsius. And then finally, we have the mesosphere, which is the solid part of the Earth's mantle, which is lying between the asthenosphere and the core. The Earth's geochemistry can be basically resumed to iron, oxygen, magnesium, and silicon. We have more than 80 chemical elements that occur naturally in the Earth and its atmosphere, and mostly Earth is composed of three parts. So the crust, the mantle, which is upper and lower, divided into upper and lower, and we have the core, which can also be subdivided into inner and outer core. The Earth's crust is a thin layer of rock that floats on the mantle. The Earth's crust is made mostly of oxygen and silicon and contains silicate minerals such as quartz, aluminum, iron, calcium, magnesium, sodium, potassium, titanium, and traces of 64 other elements. The upper mantle is made up of iron and magnesium silicates. The lower mantle is mostly silicon and magnesium sulfides and oxides. The core is mostly iron and little nickel and traces of sulfur, carbon, oxygen, and potassium. The outer core is very hot, between 4500 and 1600 Celsius. That is always molten rock, so liquid molten hot rock. The inner core is even hotter. It reaches up to 7,000 Celsius, but it stays solid because the pressure is roughly 6,000 times greater than on the surface. The Earth's mass distribution between the crust, the mantles, and the core subdivisions can be described as below. So the inner core has roughly 1.7% of the Earth's mass, while the outer core has roughly 30.8%. The limit between the core and the mantle represents roughly 3% of the Earth's mass, while the lower mantle and the higher mantle, upper mantle, is most of the Earth's mass, between 49 and 15% respectively. And finally, for the ocean crust and the continental crust, between the two, we have roughly a 1.5% of the Earth's mass. So 99% of the Earth's crust by weight is made up of just 8 elements, and these elements' composition is oxygen, silicon, aluminum, iron, calcium, sodium, potassium, and magnesium. The geochemistry of the Earth's process what we need to understand, as we've seen in the first lessons, is that the geochemistry is the study of the composition of geological materials and their behavior of individual elements is based on any geological processes as seen within the rock cycle. So between an element between the sediments, its deposition into a sedimentary rock, when it is reheated and deformed, becoming metamorphic rock, and moving on to magma, being reheated and molten state to igneous rock, and weathering, the geological geochemistry of the elements changes. So the geochemical analysis is now a vital tool in most fields of geological and environment research. And these studies for either the water, soil, and air quality, the formation of rocks and minerals, the fossilization mechanisms, and the metal accumulation in organisms from contaminated water and soil. The geochemistry domain can be subdivided into subdomains or sub-studies, and these include isotope geochemistry, which is the determination of the relative and absolute concentrations of the elements and their isotopes in the earth, on the earth's surface. We have everything that has to do with soil, so trace element, petro, soil, sediment, and marine geochemistry, which is the examination of the distribution and movements of elements in different parts of the earth, so between the crust, mantle, and hydrosphere, and in minerals with the goal to determine the underlying system of distribution and movement. We also have what we call the planetary or cosmos geochemistry, which is the analysis of the distribution of elements and their isotopes in the cosmos. We move on to the biogeochemistry, which is the field of study focusing on the effect of life on the chemistry of the earth. We then have the organic geochemistry, which is the study of the role of processes and compounds that are derived from living or once living organisms. And in verse, we have the inorganic geochemistry, which is the study of non-living organisms. We have aquatic geochemistry, which understands the role of various elements in the watersheds. And finally, for us, we have what we call the regional, environmental, and exploration geochemistry, which represents applications to environmental, hydrological, and mineral exploration studies. So coming back to Mr. Goldsmith, he is considered to be one of the founders of the modern geochemistry and crystal geochemistry, and he based his studies on the chemical elements known or represented on what we call the periodic table, and which he subdivided or classified into 4 groups according to their preferred host phases. These are known as the lithophile, siderophile, chalcophile, and the atmophile. So if we look into them, this is the classic periodical table with Goldsmith's classification. So in dark red, we have the lithophile elements. In pinkish color, we have the siderophile with the dash. We have the chalcophile, and finally in gray, we have the atmophile. So to understand this subdivision, we'll take them one by one. First, we'll see them among themselves. So based on Goldsmith's classifications, we can see that these elements were divided on how they partition between coexisting silicate liquid, sulfide liquid, metallic liquid, and gas phase. So the gas phase are what we call the atmophiles or atmosphere. So it combines the noble gases, including hydrogen and helium. We have then the lithophile, which are the silicate liquid, which combine everything that has to do with the alkalis and the alkaline earths. Then we move on to the sulfide liquids, which are known as the chalcophile, which combine everything known within metals such as copper, zinc, galena, silver, and so on. And finally, we have the metallic liquids, which are the siderophile, which combines iron, cobalt, nickel, and so on. So taking them one by one, the lithophile elements are mainly concentrated in the crust and are known as rock-loving elements. So they are distributed within rock elements. So they are close to the Earth's surface. They combine readily with oxygen, and they form compounds that do not sink into the core. These elements include aluminum, calcium, potassium, magnesium, sodium, oxygen, silicon, and titanium. The litophiles are found mainly in silicate minerals and make up 93% of the crust by mass and constitute the common rock-forming minerals such as quartz, autoclase feldspar, plagioclase feldspar, the biotite micas and muscovite micas, hornblende and fibolite, the augite, which belongs to the pyroxene, olivine, garnet, and the clay minerals such as kaolinite. If we move on to the siderophile, which are mainly concentrated in the core, are what we call the iron-loving elements. So they have high-density metals, they sink to the Earth's core, and they do not combine with oxygen. They also dissolve in iron as solid solutions or in the molten state. They mainly include gold, iridium, iron, molybdenum, nickel, and platinum. The chalcophile elements are found as trace amounts in the crust and are the ore-loving elements. So the ones that are searched for by prospectors. So they combine with sulfur. They form compounds that do not sink to the core, and they make up just about roughly 0.05% of crust by mass, concentrated in mineral veins. Examples of chalcophile elements are arsenic, cadmium, copper, lead, silver, sulfur, tin, and zinc. The atmophile are concentrated mainly in atmosphere and hydrosphere, and that's what we call them, the atmosphere-loving elements. They're known as volatile elements, so they are the most changeable ones. They occur in gases and liquids close to the Earth's surface. Examples of atmophile are the carbon, hydrogen, nitrogen, argon, helium, neon, krypton, and xenon. So how do we use all these elements and all the basics of geochemistry for geological exploration? So this is the next part. So what we have to understand here is the exploration challenge has changed through time. Until the two decades ago, geological exploration was restricted geological exploration was restricted to easily detectable outcropping mineralized bodies. So through time, what could be found on the surface, most of the mineral deposits are found. There could be some still to be found on the surface, but we have to dig deeper and deeper to find new deposits. So this is how the geological exploration is used. Nowadays, exploration leads to deposits that are not exposed to the surface and therefore are difficult to locate. So for indirect exploration, different methods were developed for the detection of hidden mineralized bodies. Geochemical prospection based on established principles of geochemistry, cycle, and distribution of elements is crucial in these studies. So Geochemistry exploration applied to mining has three main purposes. It will help to search for metals in different adjacent parts to a known deposit, defining its limits, reiterate and find new mineral bodies. It will help also finding deposits in unexplored areas, and finally help to characterize the definition and delimitation of mineralized belts and or metallogenic provinces. So how do I explore for mineral system? How do I find more gold within an area when I think from the surface I cannot see anything anymore that has not been discovered? So geochemistry has a direct connection to the commodity that is sought. Geophysics, though indisputably useful, as we've seen 2 weeks ago, it cannot make the same claim. Geochemistry is directly linked to the commodity we want to find. The geochemical responses are often larger than the target itself, so that's where we have to be careful to make sure that the anomalies we found are related to an element and not a contamination within the environment. Geochemical exploration is easier and cheaper tool than geophysics. Mainly, what we ask ourselves when we want to use the geochemical exploration is the why question. Why is the ore body there? Why is an ore body found in this area? The next question we need to ask is where? Where is the next ore body? So the why and the where are very crucial within the geochemical geological exploration. So how do we answer that? Is by adding new data, and that's what we call the data integration. So from all the data that we can take from the field, either our observations from samples, we then send that to the lab. We have new data coming in, the analysis, and we use some software to help us crunch these data and use to interpret, and we include them then in our 3D analysis or three-dimensional analysis. So we'll see this for the rest of the lesson. So among the fundamental principles of geochemistry is the recognition of geochemical environments that are developed in the Earth's crust and are grouped into either surface geochemical environment, known as supergene, or secondary or exogenous. Geochemical reactions are based on natural occurrences such as weathering, erosion, sedimentation, and soil occur. And these are clear superficial conditions and features such as low temperature and pressure, free fluids movement, and oxygen, water, and carbon dioxide present in the studied area. Another principle that is important is the principle of dispersion. Formation of a mineral deposit with a certain distribution of the ore, minerals, or elements are associated with what we call a halo around the deposit, which is formed from few centimeters to kilometers of extension. There are two types of dispersion. They're known as the primary and the secondary dispersion. The primary dispersion involves all emplacement process during the formation of how the mineralized body was formed. The secondary dispersion involves the redistribution of primary models by any subsequent process, often under low temperature and pressure conditions. Both types, they depend on what we call the geochemical mobility of elements, which by itself depends on the mechanical properties. Is the mineral that we're looking for mobile or not? And this will depend on its state and traits such as viscosity, solution, size, shape, and density of the grains, and the physical chemical features of each element. So here we have what we call, what we see here, the difference to understand between primary and secondary dispersions. So the primary dispersion is always around the main ore body, and the primary halo is the geochemical reaction between the ore body and the ground rocks or soils around the ore body. As the conditions walking away from the ore body changes by either temperature, pressure, and water circulation, we have a halo forming from different um, either gain or lost uh, in certain elements. These dispersion walks away from the ore body, and depending on the terrain we're studying and how the elements are being canalized, there is a secondary dispersion halo that is formed naturally. So we may sample material derived from the rocks on the assumption that if the rocks are enriched in metals of interest, the derived material will also be enriched in that metal. So even if we have a main ore body, the dispersion, the secondary dispersion may create another area which would be interesting, which would have a concentration of the search for metal. If we look at this same principle but in 3D, we see on the surface here on the ground we have our trees and plants, we have our stream sediments, our lakes, and right under the surface we have our soil profiles and the overburden. And right under here we have our mineral deposit hosted within a specific rock. That specific rock will enclose what we call the primary dispersion halo. So the geochemistry between the mineral deposit, the primary dispersion halo, and the secondary dispersion will be away. So this would be proximal and distal. The geochemistry would indicate us if we are near our mineral deposit or if we are far from our mineral deposit. So mineral deposits represent anomalous concentrations of specific elements, usually within a relatively confined volume of the Earth's crust. So what we see here. Most mineral deposits include a central zone or core in which the valuable elements or minerals are concentrated. So that is why it is called the mineral deposit. And the zone surrounding the core deposit is known as primary halo or anomaly. And that would be the proximal, so close to the deposit. The secondary dispersion would be the distal or away from the deposit. So we see the same phenomenon here within solid material derived directly from the rock as soil or sediment, created by the mass wasting of soil into streams or sediment on which metals would be transported in solution, so either into the ground, into creeks or lake areas. And these precipitated are the water themselves. So we can see again here from the top how these fluids would be transported using the natural terrain, slope of the terrain, and how these would leave around some either proximal or distal halos, and depending also on the traps, if they would be trapped on the soil, if they would be trapped in the stream, or trapped within the lake area. So coming down from the stream within close opening between the lake and the stream would be the most enriched part of these elements, and walking away would have less of these elements. Same thing underground. We have our ore deposit here, which is a copper zinc ore deposit. We have our halo, so our primary dispersion around the ore deposit. As we are going away or distal, with the groundwater circulations and some fractures and other structural phenomenon, we can see a secondary halo or a dispersed halo, which could indicate another of these deposits. So here we have an example of material that would be transported by glaciers or stream or lake sediment. So same logic. We have from the surface here the geochem anomalies that were taken. We have our till deposit and the bedrock with the elements that would be analyzed and the anomalies. It would trace back to either undersurface or underground to the main ore zone, and the halo would be our trend towards that ore zone. So we're going to go through some of the methods now to see the change, how regional prospecting has changed back from the 1850 to nowadays. Some of the sampling techniques didn't change. Mainly what changed are the analysis methods in the labs. So why do we use geochemical exploration? As we stated before, until 20 years ago, geological exploration was restricted to easily detectable outcropping, mineralized bodies. However, today, exploration has led to deposits that are not exposed to the surface and therefore are difficult to locate. So the purpose is the possible discovery of geochemical anomaly, or area where the chemical pattern indicates the presence of ore in the vicinity. So these anomalies, they can either be an area that is enriched or has been lessified from some certain elements. So it could be a positive or a negative anomaly. As a result, geochemical exploration focuses on the determination of the elements of the ore or elements associated with the ore that are dispersed. And these are called either indicator elements or guide elements, or more like pathfinder elements. So, example, if someone is searching for a deposit, a lead zinc deposit, the indicator elements are logically lead and zinc. Possible guide elements for lead and zinc, through studies, we've seen that mercury is a good guide element or pathfinder. Same thing would be said for many of the gold deposits are usually associated to arsenic. So the indicator element would be the gold, and the possible guide element or pathfinder would be the arsenic concentrations. So the different types of studies performed by sampling elements are either lake and stream sediment and water geochemistry, the soil geochemistry, till geochemistry, rock geochemistry, gas geochemistry, and finally the vegetation geochemistry. So these will see some good examples. If we start with the lake and stream sediment and water geochemistry, we have to understand that this method of sampling either the lake sediments or waters is ideally suited to larger scale regional projects that mostly are done by government or large major companies. And some prospectors could not carry them for such big regions. They could use the same techniques, but for smaller restrained areas. What I'm showing here is that there is a lot of provincial and federal governments that have available databases of these lake data samples. So this shows the coverage for the Geological Survey of Canada. For the lake and stream sediment and water geochemistry, what we need to understand is first, for lake water samples, it's basically using the Nalgene bottles to not contaminate the water. The lake water samples are collected in those bottles, and they're normally done before collecting sediments so that we don't have any sediment element in the water, so that the water is collected from undisturbed ponds. The The lake and stream sampling should be considered as a first pass method that can be used to identify targets prior to more detailed geochemical work. So it can either be done at first or by prospecting. On the right, what we see is once we have our water bottle samples, we can then take our lake sediment samples from what we call the Hornbrook Bump. It's like a channel that is put within the lake sediments, and the uh, sample is taken out and then secured so that it is not contaminated. What we use for soil geochemistry, we have the tools here on the side. We have what we call the Dutch auger, and we have the aluminum tags that are fixed to the ground, and with the tags that are put on the bags. So what do we take for the soil geochemistry? Basically, from the soil profiles, classic profiles within the A, B, and C layers. The A is the one that is rich in organic material, and neither of these, the AH and the AE, should be sampled because that is not what we are looking for. We are looking for what contains the less contaminated area, which be the brown B horizon, and is the main prospectors layer that is sampled to analyze for metal enrichment. We have then followed by the base of the soil profile, which is the C horizon, which consists of unweathered source material of soil. If we have a look at that soil profile, so you have the O, which is really the first 0 to 5 centimeters here, which is mainly your organic debris with little mineral matter. And then you have the A, which is your oxidized, bioturbated, and organic debris, followed by the B, which is the one prospectors are looking for, which is affected also by groundwater, vegetation, so the roots, and oxidation. Finally, we have unweathered mineral matter, which is the C. How the soil geochemistry samples is done is the same way as the geophysical sampling we've seen 2 weeks ago. We need to build a grid, and this grid has to be systematic, equidistance in the line traverses and equidistance in the sampling distance between each sample. We need to do this to not cause a bias in our analysis coming back from the labs, and we need to have a constant distribution of our materials. So soil sampling may be a second stage prospecting procedure used to follow up drainage anomaly, or may also constitute the first geochemical work to be carried out if mineralization is already known to occur nearby. Soil samples are laid out on a grid, normally in the form of irregular spaced cut lines. Sampling lines are spaced so that any important feature should be cut by at least 2 of them. Samples are spaced so the key feature is sampled in at least 2 adjacent samples. And normally this means that the spacing between the samples is much less than the spacing between the lines. So samples are spaced at intervals between 10 to 25 meters, while the lines are sampled between 100 and 200 meters apart. For till geochemistry, till is the sediment from the movement of glacier ice over the land surface and the plucking and grinding of the bedrock. So typically unsorted, meaning the fragments of all sizes are intimately mixed together, as how seen here, exposed from a road cut, We can see all the till materials here, from little gravel size to block size, is all mixed together. The till geochemistry also implies that we add on some of the ground's logical observations from the glacier. What we need to do is we need to overlay any observations from the striation directions of any glacier. And this can be seen or observed on flat rock or outcrop. As the glacier goes over any rock outcrop, the material that is between the glacier and the rock, which is mainly the till from any size, grinds or scratches the material of the outcrop, and this will cause these irregular lines as you see here. And we take our compass, we take a direction, and this will create our striation direction map. These are used to help us analyze or superpose the elements analysis and see how the lower to higher concentrations movements are within an area. So the interpretation of till geochemistry here requires knowledge of the glacier history of the area, in particular the directions of the ice movement. Usually the ice movement direction is generally towards the coast, but large and small scale deviations from this rule are not uncommon, because we have had several glacier eras, and these might have caused some of these movement deviations. Several field methods are used to determine the direction of ice movement. Most common is to measure the direction of striations on glaciation rock surfaces, and downloadable database of striation measurements exists also from the government's databases. An example here, if we zoom in a sector, we have the beryllium concentration coming back from the lab. Again, like the geophysics maps, any maps we use, we try to go from from colder to warmer temperatures colors. So all our ground noise or no anomalies to warmer colors, which would be our anomalies. So what we see here, just looking at the colors without even looking at the numbers, we see that we have two major areas with our higher anomalies, here and here. If we try to interpret them without even having the geology under, we could say, well, these two are aligned. So why are these two aligned? If we overload the ice movement, we can see that logically the ice moved from here to there. So this would explain that movement too, and also the shape of these anomalies. So here is an example of the glacial dispersion of the beryllium from the Strange Lake area, and shows the metal deposit. Same example using the till geochemistry, using a plan view from the surface and several little illustrations of cross sections perpendicular to our main area. Then using also a longitudinal looking north to this area to have a complete overview. So again, these will show areas that have the highest anomalies. These anomalies are then grouped together or interpreted together, leading to an ore zone area. So schematic sections and plan of glacial dispersion from an ore zone are very helpful to help us assume how the till deposited the main events. So the distance up ice to the bedrock source of a geochemical anomaly or mineralized boulder detected at the surface is dependent on the till thickness, as we can see here. Within all our sections here, we can see that these are moving down towards the ground, and this is what we are representing here. So how do we do geochemical mineral exploration? So here what I wanted to pinpoint is the main steps and just give you the generalized steps. So first we need to select the geochemical survey study area. So just like the geophysics and the cartography surveys, the main purpose of this stage is to select areas or regions that have good mineral potential and that can be prospected effectively. Initial selection of areas should be based on a most thorough review of the known geology and records of past mining and prospecting activity. To get some idea of background for an area of interest, prospectors should examine regional and local historical survey data with respect to their area of interest. So even if we're going out on the field in a new place we have never worked out physically, we always need to, before going out on the field, try to consult the historical work, either geology, geophysics, geochemistry, and this will help us try to understand the area. So based on recorded mineralization and on the geological environment that we are studying, that's how we're going to choose which geochemical survey we are going to do and how it's going to help us define the steps. First step, which survey scale we're going to use. Just like the geophysical and the cartography surveys, we need to know what we are looking for. Are we looking at something that is huge, that is a mapping large crustal blocks within tectonic assemblages? Are we working in a continental scale, regional scale, or just a local scale? So as you can see, the numbers vary a lot. From continental scale, between 500,000 and a million scale, or going down to local scale, which is under 150,000 scale. So the scale at which we need to do our survey is very important. Then we need to characterize the target size and the geometry. That goes with the scale too. Some features of ore environment, such as the what are the favorable host rocks, the geological structures, or the geochemical provinces that are related to the genesis and localization of the metal we are looking for. Each geological, geophysical, and geochemical features of the ore environment defines a target area of characteristic size, shape, and relationship to the ore. So we need to know exactly what we are looking for to find it. We need to use, once we know what we're looking for, we need to use the right exploration technique. So for greatest overall effectiveness, an optimum balance must be struck between the various geological, geophysical, and geochemical methods that are known to be applicable. The choice must be based on relevant previous experience and case history data. We need to fit with the chosen scale of the study area, and finally, the selection of methods is also strongly influenced by the size of the target and by the property control. We need to rely on the chosen geochemical survey methods. So the reliability depends not only on how effective the exploration method is in locating the target, but also extent to which an anomaly is specifically related to the ore and the abundance of non-significant anomalies that may confuse interpretation and require follow-up surveys. We need to link the cost of the method based on the value of the expected ore. If we're looking for gold, our budget would be higher than if we would be looking just for, let's say, silica. So the expected value of the ore body being sought and the chances of success may have an appreciable bearing on the applicability of a given method. A highest cost survey is justified for large ore bodies are expected, and there is relatively little chances of overlooking a deposit. Conversely, a low-cost survey is justified in areas of small targets. We need to assure a high quality control for geochemical surveys. Geochemical methods of exploration constitutes an important tool in the investigation of the economic mineral deposits. Any geochemical investigation, to be effective, must take into consideration several aspects of the ore body, including genesis and cost at various stages of exploration. Okay, sorry about that. So to assure the high quality control of geochemical surveys, okay, just give me a second here. Okay, so to justify the role of geochemistry in an exploration program, what we need to do is to make sure that geochemistry is an essential component in most modern integrated mineral exploration programs for two reasons. Economic mineral deposits are commonly characterized by their low grade and large tonnage. So the discovery, assessment, and development are highly dependent upon geochemical methods and analysis. Exploration activity is mostly carried out in tropical and subtropical environments, where chemical weathering has predominated, where geochemical prospecting techniques have proven most effective. So recent estimates suggest that between 10 and 25% of exploration budgets are allocated to geochemistry. The elements to analyze, how do we choose them? We need to separate them in three categories, either primary targets, secondary targets, or pathfinders. The primary targets are the metal elements that are most commonly sought by prospectors. Example, gold, copper, zinc. Secondary targets are metals, except fluorine, which may be sought under special geological and economical circumstances. For example, specific metals within the platinoid family, which are sometimes sought after within cycles, within centuries, cycles, depending on how we need them for industrial development or not. Pathfinders are uneconomic elements that are useful in discovering a deposit of an element other than themselves. So usually the target have sampling or analytical challenges that the pathfinders do not have. Example, for gold, arsenic is an excellent pathfinder. So here we have a table showing the main primary targets, secondary targets, and their pathfinders. So primary targets include precious and base metals such as silver, gold, chromium, copper, molybdenum, nickel, lead, platinum, tin, uranium, tungsten, and zinc. Within the secondary targets, we have specific elements such as barium, beryllium, cesium, fluorine, mercury, and all the rare elements, lithium, niobium, palladium, rhodium, etc., that are used for specific main industrial purposes. Finally, we have some of the main pathfinders, such as the arsenic, boron, bismuth, cadmium, tellurium, and thallium. When we do the geochemical mineral exploration, we need to reduce any nugget effects. Gold is one of the elements that is known to have a high subject to have nugget effects, which can cause an anomaly to be missed or alternatively unrealistically high values to be returned in an area which is not representative. So as we see here, this illustration, it shows that the gold sample material represented by the smaller square, which is here, which is the background values, which are the lower value, which represents really the area. If we pick within the smaller square here, we will have what represents the very low assay. If we pick within this area, within the high gold value, the overall value, general medium value, would be higher. But this value would be caused by the nugget higher sample that we have here, which would not be representative as we see of the area. So as indicators of the bulk gold composition of the sample, neither would be correct. A pathfinder element like arsenic is more evenly distributed and not subject to this problem. So it would be good to superpose within gold analysis within our samples, also to have the arsenic analysis. We need to understand our analytical certificates coming back from the labs. So for this lesson, I did not include all the specifications. This could have been another complete lesson apart. But what I mainly wanted people to retain here is that coming back from the labs, we have certificates that gives us the number, which are the analysis results. And these will be accompanied by signs like lesser than signs or greater than signs. And these are based specifically on the threshold of a sample. This means if we have a lesser than, it means that there is so little of the element in question in the sample that the analytical method that was chosen from the lab is not sensitive enough to measure it. So the threshold sensitivity is lower than the method that was chosen. The negative sign or the less than sign is sometimes replaced by a minus sign, and rarely we have an ND, meaning it's so small or so low it was not detected at all. We have also the reverse, which is the greater than sign, which indicates an analysis that exceeds the method's upper range. So that often happens with higher concentrations, especially with gold. If we have 10 gram and more, we need to change the method to make sure that we have the exact analysis for the gold. I'm going to go through now some slides that were given to me by us, Geoscientific Services, like we've done with the geophysics studies 2 weeks ago, mainly with the work from Abitibi Geophysics, which are the main consultant within Quebec and Ontario. Same thing for everything that has to do or apply with geochemistry within Quebec, and most of the country, most of Canada, are using the IOS Geoscientific Services, which are based in the Chicoutimi and Val-d'Or area. So before starting any geochemistry survey, we need to go through the field surveys. So once we have field surveys and we have areas we pinpointed we want to go back and have more specific work, we go and we bring in any machinery we need to bring in here we want to get rid of all the moss and everything from the rocks and all the soil to be able to go and see the complete outcrop. So what we call here the helicopter outcrop stripping, because the stripping tool is brought in by a helicopter. Everything is done in compliance with all the environment regulations. This stripping is taking away all the soil and the ground above from the rocks outcrop. We then do a trenching and sampling survey. Sampling is done randomly as trenching can be done systematically, covering equidistant surface of the outcrop. We then go from sampling of lake sediments, again using helicopters. IOS has covered more than 50,000 lakes from all their consultant work. We are showing here some of their sampling, characterization from either surface water or lake sediments. We have till sampling, which is done basically with a shovel. Shovel is going down to make sure we're under the soil and we are within the till quaternary geology element. We then have the soil sampling and how we are taking our soil sample to be careful to not cause any contamination within our sample and back to the lab. So IOS have a lot of experience in soil sampling and characterization coming from either trenching sampling, drill hole sampling, collecting soil samples, and also back within the tailings and abandoned sites. They have a high experience also from everything that has to do with P.Geo, geochemistry, which is related to the soil, and also from their labs, either from the preparation of the soils and their lab, how they're handling the samples to make sure that between the field and the lab, everything is done super clean and reducing any risk of contamination. So going through their methods, I just wanted to pinpoint some of the general things you have to be careful when you plan any exploration geochemistry surveys. So I'm going through mainly how to plan, to interpret all these samples. So first of all, the planning and sampling. What can influence the planning and sampling of our survey? So as we've covered so far, we saw that the medium adapted to the context. So everything is influenced by the regional or local scale, by the environmental type, the availability and homogeneity of the elements, and which is the targeted metal. We've also seen that we use the most suitable medium, the right analytical method for the medium, and the one you master the most. We have seen that depending on the technique and the scale, we can have a difference between efficiency and cost. The main problems within sampling for either quality or errors are due from sampling. So these errors are mainly due to the project manager, and the main errors that can come out are the numbering errors, the localization errors, bad material, that means we're not taking the good material from the field. We don't have the right description of the material. We don't have the description of the environment where it was sampled. We have induced some contamination problems. We are using poorly trained staff, and we're not very robust with our working method. The numbering, if we start with the numbering, a lot of errors come up with numbering our samples. As simple as that. The most serious errors is if there is an anomaly, the tracking takes place in the wrong place. So right away, the numbering leads us, we can have the biggest anomaly from the lab. If we cannot go back and localize it well on the field, we are completely lost. Some of these major errors are between either our manual and digital manipulation of these numberings. So we try to avoid letters. Why? It's because from manual to digital, depending on some of the softwares, the letters are being taken off when we import our data. So we try to maintain, uh, avoid any complexity and maintain our numbering as simple as possible. Example here, they're showing a numbering system using the project number, the code for their soil sampling, and their sample number. So someone looking at this number from a company knows that their project number is 929. They know that if they use soil sampling, it's their codification 5, and then they know their sample number. They try to use now more and more what we call custom coupon books with barcodes, so that the number written on and the barcode, so either from manual to digital manipulation, there would be no errors whatsoever. And these barcodes are scanned, increasing the process time and decreasing the errors. The location is this number 2 or equal to the numbering errors. If we cause a location error, again, we can have the biggest anomaly in the world, but if we cannot go back to it, it is not worth anything. So we use more and more the GPS to be able to localize our samples. Again, the GPS is very precise, but if we are lost in the coordinate system we are using, example here between NAD 27 and NAD 83, the difference can be in easting and northing between 50 and 250 meters. The location will help us plan the traverses for soil sampling. Big errors can be done between the digital and handwritten notes. So if we're not using the GPS, that's another way that we are going to cause some errors in our coordinates. And our station numbers that we are putting in our GPS, also putting in our data from the field. We can even cause some errors there on the field before going back to the office. The material selection. A part here, this is really has to do with what do you want to sample. Any sample can be sent out to the labs, but if we're not sampling the right material, any analysis coming back would be false analysis. So the quality of the survey depends on the homogeneity of the medium collected or the sample collected. So samples represents material other than the targeted material. It must be performed by trained employees, not just supervised. Some of these results can be as fatal as garbage in, garbage out, meaning if you don't sample the right material, whatever results you have coming back would not be useful to define any new deposits. So the material selection also depends on the meaning of the geochemical signature on the study area, and therefore depends extremely on its environment. The sample environment must be adequately described. Again, it's very expensive to do afterwards. This has to be done simultaneously while on the field, while sampling initially. So the person sampling needs to know how to describe everything that is around the sample. So this includes the topography, the slope, the drainage, the hydrography, the forest cover, the geomorphology, the outcrops, and so on. The soil profile, the anthropogenic influence, and everything is used to eliminate false anomalies, because each anomaly that results from the lab has to be explained. Every anomaly has to be explained logically. So any anomaly, the first step we do is we need to know where or what is the ground. So what is the general content within that ground? So how come this is an anomaly, either positive or negative? What causes this anomaly? So we need to describe the sample. Again, very important. Just like any work in geology, uh, every description is used and necessary for any interpretation and is required for any QA/QC, so any filtering of the results. We need to know what is the granulometry, what is the color, what is the humidity, the cohesion factor, the constituents. Is it silt, sand, gravel? What types of pebbles? What are their size? Are they centimetric? Are they metric? Is there glaze? Is there any organic matter within the sample? What is the crust of the sample? And so on. The color. Color, again, if we want to be able to work with color, we need to get rid of anything that has to do with subjective colors. Subjective colors being from one person to another person. A same color of brown can be discussed as red brown, goo poo brown, or chocolate brown. But this is not useful in a database. So that's why now people are using what we call the Munsell colorimetric chart. And this chart is used with RGB codes. And these codes are the ones that are put in our systems. So this is not subjective, but mainly used to uniform this quantitative characteristic. The sample size. Sample size vary depending on the technique we want to use in the lab to analyze and what material we want to analyze. Example here, if we're using cationic methods, we just need between 300 and 1,000 grams of wet sample. If we're using chemistry for digitotrical fractions, these would vary from 300 grams for fine granulometry, 1 to 5 kilograms for bleg, and 10 kilograms for heavy minerals. For mineralogical methods, if we're looking for areas which are enriched in high concentrations or nugget gold, we need to have at least 10 kilogram samples. For tills, we need between 20 and 30 kilogram samples, and for F.N.Q.L.S.D.I, we need between 20 and 50 kilograms samples. The optimal scales of surveys and the resolution of the analysis back from the labs vary and is based again directly on the scale between local and regional scale. So between local and regional scale, the methods are used between soils, streams, tills, lakes, rivers, and estuaries. So if we're working on a local scale, we're going to go more within soil geochemistry. If we're working with regional analysis at first, we're going to vary between rivers, estuaries, lakes, and so on. And this would also be defined on the transport distance of the material within a known area. So the more the material is transported towards less transport distance, the methods are going to change. And from the data resolution between cationic and digital studies, these methods will also change. For lakes, mainly we have mileage spacing or kilometric spacing, Heavy logistics. We try to avoid sampling near riverbanks, mouths, or in bog lakes. We use helicopter torpedo sampling, which is called blind sampling, which is basically done covering the entire water area. Tight sampling of a same lake is not useful since the lake is closed and has no contamination from any water beds. River and estuaries are pluri-kilometric spacing. Um, they are mainly silted and clean gravel, containing heart of the estuary or swimming pool in the rapids. Avoid shoulders or sandy dunes. They show rapid dilution of chemical signal. They're mainly done within oxidizing systems, which does not contain sulfide, and heavy mineral studies only. For streams, which are detrital, they are used within sub-kilometer spacing. For alluvial plain and meanders, areas where there is high energy zone like confluences, rapids, and traps, which can be sectors or areas with higher concentration of heavy minerals. They are used for mineralogy or chemistry and within the oxidizing mediums, so destroy the sulfides. For streams, for organic banks, they're mainly used for flood zones, organic material, absorption of water cations, and restricted watershed influx. For glacial sediments, for detrital elements, mainly using bottom and melting till. So these need to be consulted with and for what we call the geomorphological study or specialist, which is a quaternary geologist. And these would include any study of material availability, the flow direction, the complex stratigraphy. We have to understand that it doesn't work everywhere, and used within the presence of wind, glacier, or runoff. We need to have samples between 10 and 30 kilograms, and the chemical analysis varies between 0.5 and 2 kilograms. The fence of the study area should be between 2 and 20 kilometers perpendicular to the dominant flow, and the spacing on these fences should be according to the target. For soils, only local grid methods are used. The line should be between 100 and 400 meters. The station between the sample should be between 25 and 100 meters, so it's a 1:4 ratio between the sample station and the lines. And these should include different horizons to characterize their difference in signature between layers A, B, and C. So for soil sampling, the method is simple. We just used an inverted plastic bag used as a glove. For each different sample, we use a different one to avoid contamination. We just do a hole across the horizon that we need to sample. We transfer the material from the plastic bag to a craft paper bag, one per sample. We never use two for two different ones. And we include the barcode labels that will be laid on the field with the sample number, and transfer that sample number also on the paper bag. For soil sampling within the organic or peaty soils, we need to dig deep to make sure that we are within the fibrous soil or the organic peat soil. The soil profiles as seen in reality when we dig a hole to make sure we are in the right area. So we have the fibrous material or the organic material between the first few centimeters, going down to the humic and leached area of layers A, AH, and AE, as seen here, going down to the ferruginous zone, which is the main zone for prospectors and can be recognized by its color, either orangey, yellowish, reddish, depending on the iron content. And finally, under the layer B, we have the C, which is the non-altered overburden. We have also, within the pod soil of the soil's profile, we can see areas where are leached soil, so poorly developed. They're typically thin and dominant on the tills. They show very acidic environments within cold climates, and they are typical of the forest floor of the taiga with conifers and ericaceae. They are dominated by the chelation and organic iron aluminum complex, and the horizon B is poorly developed in those areas, and it is very easy to sample. Within the bruni soil of the soil profiles, they are very well drained soil, mainly within hardwoods and pine forests. They are very permeable terrain because they include sand and gravel. So they are dominated by downward flow of the water circulating in the area. They are considered to be within oxidizing environments, so intense ferrochelate with a high developed horizon B. They have a complex structure that can be thick, and they don't have any leach zone AE. They are easy to sample humus. The horizon D can be difficult, but the presence of the fairy crust and the destroyed forest fires are common areas for this bruni soil. The bruni soil can be subdivided between the fairy crust and the hardstein layers. The glacial soil is completely opposite of the bruni soil, so they are mainly waterproof land with the argile. So they are waterlogged soil within swamps, bogs, sphagnum, moss. They are poorly drained, and they are within an anoxic reducing environment. So they don't have any ferrochelate, they don't have the horizon B, and they are enriched in clays. The humus sits directly on the clay. They can be deep. We have to sometimes go down to 1 to 2 meters, so we need to use the Dutch auger tool to dig them up. The alluvial soil is a leaching soil, mainly within the agricultural plains or fields, and they're just covered by the herbaceous plants. They have a good drainage, the weathering and productions of clays. They have a good positive water balance dominated by downward alluviation or eluviation water circulation. They have a complex structure, and they're pretty easy to sample and can be thick and disturbed. Finally, other types of soils that can be sampled can be divided between the molly soil, which is the accumulation of organic matter in herbaceous plains. There is the poorly developed profiles, which is the irregular soil, the cryosol, which is mainly for permafrost environments, the vertisoil, which is clay soils with poorly developed profiles and argilo-pedoturbation, and finally the fibrous soil, which we've seen, which is related to the peaty soils. I've included a good website here that describes very well each type of soil in Canada. So now that we have seen all the techniques used for geochemical sample exploration, how do we use all this data, and how do we use it, and what is it useful for? So Data for major elements are generally reported in the form of oxides as weight percent. So example for silica, it will be shown as a SiO2 percent. Trace elements will be shown in parts per million in ppm. We can also have in parts per billion in ppb or micrograms per gram. An important consideration in the interpretation of data is analytical uncertainty, particularly when evaluating the existence or significance of small variations in composition. Some of the most common sources of certain uncertainty are sample contamination, incomplete sample digestion, some minerals are extremely resistant to acids, and interferences between elements and poor instrument calibration. So we have to be careful here again with the lab results, with the lab anomalies to make sure that they are real and realistic ones. The extent of these problems is best limited at the time of analysis by taking necessary precautions and through discussion and experienced lab staff. They are, however, impossible to eliminate completely, and an indication of analytical uncertainty should therefore be reported with the data, ideally as error bars on geochemical diagrams. So we need to add a little codification here to make sure that our data is reliable. Uncertainties can be estimated from the regular analysis of reference materials of known composition and from the analysis of two or more samples. To help in the interpretation, data are often imported into graphing and statistical computer programs. A wide variety of diagrams can be produced to compare the data with those from previous studies and to demonstrate trends or new interpretations. Example of the geochemical data that we need or incorporate in our study are either taken from the surface, so 2D, or from underground from 3D data. These include everything that has to do with the rock, so lithogeochemical data, the sediments, tills, the alteration indexes. This could have been another lesson, complete different lesson. So I wanted to show more practical uses of geochemical than theoretical. So I chose to take them out, but they will be included within the mineral resource lesson that will be from block 3. So we either have calculated indexes or from some software, and we have the lab analysis, so either economical analysis and or other specific ones. So all these are used in what we call quantitative or qualitative punctual data. So quantitative is everything that comes back from the lab that is given from an analysis, and everything that is qualitative is from an observed field observation from the technician that took the sample. So anything that was written down from either color, grain size, and so on. From the geochemical data interpretation, we have maps that we call targeting proximal and distal footprints maps. So from what that means is, comes back to what we see in the dispersion halos, proximal for the principal dispersion to secondary or distal footprints. So basically could be on graphics, could be in 3D, or it could be in surface maps or from cross-section maps. What we see is we always base our analysis or results showing where we have a known deposit and using the colder to warmer colors, we show where the anomalies are for each of the analyzed elements, compared to the physical distribution of a known ore body. So we then are able to show within an ore zone area and within what we call a proximal, so near an ore zone, to distal, so away from a ore deposit, how the geochemistry changes. So in this case here, we have an ore deposit here, we have an ore deposit here, and we see that close to the ore deposit, we have a chlorite zone. Then we have a transition between a lower chlorite zone to a potassium-rich zone to a potassium barium-rich zone, and finally to a potassium barium sodium-rich zone. So this is in 2D. When we dig within 3D with our drill holes, and we come up with our samples, and once we have this very well under control and we have our analysis back, let's say a sample would come out with a potassium, barium, sodium-rich environment, we would know that we are away from our deposit. On the contrary, if we have a high chloritic zone analysis from samples, we know that we are near our ore deposit. So, example here, same logic, same approach, what we call the targeting proximal and distal footprints, just by looking at the color from colder to warmer colors, we can see that most anomalies are situated here in this area and this area here. And then we would sit down and we try to see, is there a trend? Is there something continuous? If yes, can we superpose our geology? And is this aligned with any known structures or any known geological unit, and so on? So this would be a way to investigate and try to characterize the traits of a known deposit. Same process, looking from the surface to underground to where we have our ore. So from the surface, from everything that is covered by vegetation, so within the hydrogeochemistry, so by the water, or biogeochemistry, everything that's with the trees and the shrubs and the fields. So under 50 meters, going down to hydrogeochemistry between 50 and 100 meters, and everything that has to do with the immobile geochemistry, mineral geochemistry, and mineralogy, with the regolite sectors, and going down to the basement to the rock geochemistry, mineralogy, and the mineral chemistry. So again, the targeting of the proximal and distal footprints will lead us to know exactly where we are and if we are proximal or distal from our ore. In real-time integrated data, while drilling is also, the geochemistry is also used using some of the instruments that are called XRF. XRF we can use is like a simple gun that is pinpointing systematically within our rocks and leads out already in a fast way, fast but less precise than an analysis, where we have horizons that are richer in some of the elements we are looking for. So while we are logging and drilling, we can combine all our geological observations, such as textures, colors, the mineralogy, the petrophysics, is the rock not deformed versus deformed, is it broken down, and the geochemistry can be right away observed by the changing of the just logical colors and elements that we are looking for. We can also link everything that has to do with the geophysical anomalies maps that were interpreted and layered with another interpretation this time using the geochemistry. So as we see, the underlying map here is a geophysical anomaly map. And here we are showing the copper samples. Another way of showing the anomalies of geochemistry is also not just by the color from cold to warm, but we're also using a smaller sample size towards a bigger sample size to show that our anomalies are increasing. So right away in this picture here, I can see my background noise is within these blacker small dots, greener dots, yellow dots, and as I am increasing my concentrations in copper, my dots or circles are increasing too, and they're varying from orange to light red to dark red, and I can see my areas which are richer in copper, and I can see if they correspond to any known geophysical anomalies too. So the geochemical surveys are conducted to provide baseline information for mineral exploration, geological mapping, and baseline values for environment and land use purposes. The geochemical survey data contains various information for geological, geochemical, environmental, and climatic processes. Geochemical survey data uses more than 50 elements that can be analyzed at sufficiently low detection limits. They reflect processes that form or affect the mineralogy of the rocks within a studied area, and they represent a multivariate data space over a 2 or 3-dimensional geographic space and time. Example here of another geochemical data interpretation method. Seen here, we're within the Melville Peninsula case study in northern Canada. If we zoom in, first thing we do before going into our geochemistry data interpretation, we need to know or understand our geology. So we go on the field, we do our field cartography, and we basically show a simplified map of that geology. We can see with the legend here that most rocks are what we call from our metamorphic rocks. If we zoom in this study area, we then can do systematic sampling, geochemical sampling of the area. We chose here to do lake sediment sample sites, and one site represents roughly 13 square kilometers. If we superpose this sampling within the detailed geological units or map that we superpose both our geology and our sampling, we want to see right away the link between our geology and our mineral occurrences. So our mineral occurrences here are listed here, are given their specific sample shape and color. And right away, we can see that the distribution of these are locally based or differentiated with the known geology. So for example, our gold dominant analysis are our yellow diamonds, and we can see their occurrences, how they are spread within the area. So once we have that, we can also push that information even further by using a residual sampling based on the gold concentration. So from smaller to bigger size shape to know where are our richest gold concentrations. And this is superposed to our known geology. Same thing can be done with any other element. Example here for our nickel. and zinc, and finally for copper. So this would then be compared with our geology to know if our background unit, how does our background unit composition vary or contains that elements to make sure that they are real anomalies and not just normal anomalies compared to the rock's concentration. Once we have these, we can also push our interpretation further by transforming these in 3D illustrations to do what we call isosurfaces of an element, and the isosurface of an element within a known mineral deposit area and the known drilling in the area to try to define areas where we need to either add more drilling to increase a known deposit area. Example here of gold isosurfaces for several values or content or concentration. And we can see some areas that are richer and some of the background values. So we could then zoom in areas that are richer and try to see if there is enough drilling, or should we add more drilling to try to understand what is the shape, what causes the shape or the distribution of these richer zone areas. We can see that maybe we have folding here. Among folds, sometimes there are traps for gold. What separates these two concentrations? Is there a fault here? So that's how the geology and the geochemistry would be used together to understand these differences. Other kinds of geochemical interpretation here would be, without even using any elements, would be combining any alteration with their values coming back or calculated. Again, we see the concentration of alteration, how we have lower background values versus inside with higher alteration occurrences. And again, how come these occurrences are aligned together? How do we explain that? So every time we have an anomaly, we try to explain how this anomaly was how does this anomaly appear and why does this appear in that area and in that shape. So for the rest, for the videos, it was a bit hard for me to find some practical videos on geochemistry that were short for today. So the last two that I've included here are very good videos, but I advise you to go back on your own time because they are pretty long. There's a half hour and there's almost an hour here, but it would help you understand with practical examples. For today, I'll be showing two smaller in length videos. The one showing how to take a geochemical sample, soil sample, and the one here, the geological map here, is one that I find very good to resume the last two blocks or the last 6 lessons that we've seen so far. So we're going to move on to the videos.
The TELUS Geochemistry field programme requires the careful collection of soil samples. Care should be taken when selecting a soil sample site. Ensure the site is representative of the surrounding area. If possible, aim for a site central to your grid square, choosing undisturbed and unforested land where possible. Stay away from any evident sources of contamination. The sample site must fulfill a number of distance criteria. For example, at least 100 meters away from any features that are present or are mapped, including minor roads, streams, buildings and electricity pylons, and at least 200 meters away from rivers, large water bodies, quarries, railway lines and major roads. At the chosen sample collection site, note the exact location using your handheld GPS unit. Both samplers should cross-check the location on the 1 to 50,000 scale field map and confirm that the site meets all criteria and is suitable. Before beginning any sampling, all the large brown craft paper sample bags need to be labelled at the same time by the same sampler. Label bags with the 6-figure site number, approximately 1/3 down the front of the bag. On one, write the letter A below the site number, and on the other, the letter S. Underneath, write your own initials, followed by the initials of your field partner. Before collecting any samples, the auger must be used once to remove material from any previous site and to pre-contaminate ahead of sampling at this site. Collect one full auger flight of material and discard this material. Kick away the top rootlet or leaf litter zone before inserting the auger. The first sample is collected from the top layer of soil to a nominal depth of 20 centimeters. Ensure the auger is upright and your back is kept straight. Use a pushing and clockwise rotating motion until the top of the auger flight is level with the ground surface. Remove the auger and take note of the sample characteristics. These include colour, texture, water and organic content, class lithology and the presence of any contaminants. Describe the characteristics to your partner and note these observations. Place the sample in the bag labelled A. Return the auger to the same hole and turn it several times until the flight is filled. Remove the auger and note any changes in the soil characteristics such as colour and texture. This intermediate auger material should then be discarded. Once again, return the auger to the same hole. Turn the auger until the tip reaches a depth of 50 centimeters. This depth is reached when the coloured tape on the shaft of the auger is in line with the surface. Remove the auger and, as before, note your observations about the sample. Place the soil sample material into the bag labelled S. Always make an effort to fill the hole after sampling. Soil samples are a composite taken from 5 independent auger holes in a 20 metre by 20 metre square arrangement, with the first hole in the centre of the square, which is also where the GPS coordinates are recorded. This formation resembles the number 5 on a die. At each hole, collect the same set of samples. First, a topsoil sample from an auger flight from just below the surface, nominally to 20 centimeters depth, known as sample type A. Next, an intermediate flight, which is discarded. Finally, a subsoil sample aiming to reach 50 centimeters depth, known as sample type S. To measure the distance between sampling holes, count the number of strides taken. In order for this to be accurate, you should know your stride length in advance. Remember that your stride length will vary on different types of terrain. For every auger flight sampled, the soil must be inspected and any variations recorded by your field partner. After samples have been collected from all 5 auger holes, assess the fullness of the sample bags. If necessary, additional auger holes from applicable depths can be collected from anywhere within the 20 metre by 20 metre square to fill the bag. Note this in your observations. Seal each bag by folding the metal tab and bending the tabs to the front. Always place the sample bag into a poly bag to avoid any sample loss or cross-contamination during transportation. Before leaving a soil sample site, both samplers must ensure that all required observations and notes about the site and the samples are made. When leaving a site, always check you have all samples and equipment and that you leave the site as undisturbed as possible.
The second video, like I said, just resumes everything we've seen so far and how a geologist will use all the knowledge that we've seen so far on the field and in the office, interpreting all the maps.
When we hike through the countryside or gaze at a mountain, we have the feeling that the landscape surrounding us is unchanging. But is that really the case? We live on an evolving planet which has been transforming for millions of years, and it continues to. And don't forget that what we see on the planet's surface is just a small part of the whole. Under our feet is a wide variety of geological materials, rocks, sediments, minerals, and more. Their presence, composition, characteristics, and formation is what geologists study, and their graphic representation is what is known as a geological map. A geological map takes a profound look at which materials crop up on the Earth's surface and how each of these elements is arranged. In other words, the map is a representation of the geological architecture both above ground and underground. This vital information allows us to make the most of mineral resources such as metals and energy sources like coal and oil. It also helps us to locate the water that is filtered into aquifers and to use geothermal energy. In addition, geological maps are important for guiding agricultural activities. But that's not all. Thanks to geological studies that are supported by maps, we can establish where natural processes are likely to occur, including landslides, earthquakes, floods, and volcanic eruptions, minimizing the consequences of natural catastrophes. Actually, geologists' work begins in the library. The first thing they do is to analyze and study any existing work that covers the area where they plan to create the geological map. Geologists need an overall view of the terrain and any variations in elevation. To this end, they use pairs of aerial photos. These are partially superimposed and used with a stereoscope, allowing for a 3D view of the surface of the area to be studied. In less complicated zones with scant vegetation, photogeology makes it possible to create a preliminary map which is quite complete, accurately pointing out faults and folds, as well as classifying materials. With this preliminary study, geologists can determine which points must be observed directly in the field because they are either complex or representative in nature. And now, the field work can begin. It's not usually possible to analyze every inch of the terrain, but geologists, guided by the observations they've made using aerial photos, follow a predetermined path with key stops known as stations. At each station, geologists identify different kinds of materials. They collect and study samples of rocks, sediments, and fossils. All of these are carefully labeled, and the exact date and location are noted. The rocks that make up planet Earth, which we can see on its surface, are quite varied. Igneous rocks formed by the cooling of molten rock deep within the Earth, metamorphic rocks transformed by the great pressure and high temperatures found underground, and sedimentary rocks formed by the accumulation of sediment in lakes, in riverbeds, and on the sea floor. Sedimentary rocks are deposited in layers of varying composition as strata, usually in a horizontal pattern. In order for them to become visible on the Earth's surface, they must be pushed upward by the same forces that create mountains through a process known as orogeny. During this process, which lasts over many millions of years, rocks are deformed, folded, and fractured along break lines called faults. Using a compass outfitted with a clinometer, geologists can measure the direction and inclination of strata and other structures. This allows them to recognize different geometric patterns and gather essential information in order to make a three-dimensional reconstruction. With the help of aerial photographs, they draw a first draft of the map directly on the terrain, marking lines between the different rocks. Their observational capacity, experience, and knowledge of other similar phenomena allow them to sketch out large areas of the map. All of this information is compiled in their field notebooks or on more modern devices, which allow further data to be entered in a geo-referenced manner. Back in the office, geologists contrast the information they have obtained with aerial images and previous studies in order to finalize the map, which may or may not be digital. Standardized symbols provide visual clues to help us rapidly identify the different types of rock that have been found: sandstone, limestone, and dolomite rocks, the age of which is shown by their color. The geological age of each rock is an essential piece of data that geologists need so they can put the events that created them into chronological order and examine the geological history of every corner of the planet. The evolution of animal and plant species and the successive great biological extinctions make it possible for us to date sedimentary rocks because of the fossils they contain. Rocks with the same fossils will be the same age. The absolute age of a rock can be determined thanks to radioactive dating. When a rock is formed, the minerals have a precise elemental composition. Some of these are radioactive and therefore become unstable over time. We know that they disintegrate in a certain time period, giving way to other elements. If we measure the proportion of these, we can find out the moment the rock was created, sometimes many millions of years ago. The geological map is not just a flat representation, it is also three-dimensional. Using orientation and inclination data for strata and faults, geologists can draw geological cross-sections and 3D models that show the spatial positioning of different materials located many kilometers beneath the Earth's surface. Once the mapping process is complete, field geologists send a rough draft of the map to cartographic specialists for validation. Once it has been approved and accepted, the map is ready to be published in different formats. Since geological science began hundreds of years ago, geological maps have served as a basic tool for geological knowledge. And this is still the case. The maps are a visual expression of the work of geologists, allowing us to learn what the Earth is like today, to remember what it was like yesterday, and to predict what tomorrow will bring. For beneath our very feet, although it may be quite slow, the Earth is changing, moving, and transforming.
And so this ends block 2, lesson 3 on the geochemistry surveys. So
We're good?
we're good.
Okay, well, thank you, Francine, once again, for a really insightful and detailed deep dive into geochemical surveys. I personally learned a lot. Hopefully, the people at home learned as well. Quick reminder once again, we'll see you guys in 2 weeks. So we'll dive into block 3, mining exploration. It will be on a Tuesday, which is a slight change from our regular schedule. You'll get all that information via email. And as usual, if you have any questions regarding the material that was shared earlier today, just feel free to write us at info@iddpnql.ca. We'll make sure that information is passed on to Francine, and we'll forward that answer back to you. Until then, stay safe, have fun, and we'll see you in 2 weeks. Bye-bye.
Thank you. Bye-bye.